At the end of the day, we'll probably ask you to take bottles of water from Chase tomorrow. Water from Chase.
You know, if you're waiting.
Okay, so he makes sense.
Yeah, so I think I'm right. I think everybody's got to come back in. Let me send out the. I think I saw it as high as 8 or 9.
Conference at this time. We could offer the
reboot ones.
Test.
Hey, thanks for the presentation. It reminded me of probably one of the best times I've ever had.
Yeah, it wasn't a tough presentation. Fun to read.
You're exactly right.
Okay, we're getting ready to get going. Let's get
Yeah.
All right, everybody.
So interesting. Harold, I've been with Friday. I was thinking all of my brains as hardware.
That was such a brand new. I mean, that presentation was probably one of the best times I've ever had.
Yeah.
Everybody. Did our package? Okay. All they're on the good time? Okay. All right, so I'm between you and lunch, so we'll try to keep this as lively as we can. So again, I'm Jeff Shykula, fairly new member to Edge of Space Sciences, only been about a year. And I'm going to talk to you a little bit about a project that I'm working on, which is a software-defined receiver. The ultimate goal to be able to monitor multiple balloons and multiple beaconing frequencies all simultaneously in a small form factor, low-cost package. So quite a challenge, but it's a fun project I'm working on. And I've got some of the hardware I've been prototyping up here. Take a look at it over lunch. So the challenge I'm trying to overcome is really the, as I was saying, the increasing number of student payloads, a lot of interest in access to space, which is great. We're seeing a lot of science and technology in the classroom and easy access to edge of space through balloon launches, but it's driving a lot of multiple balloon launches. EOSS will typically be doing 1 to 4 balloon launches on any particular event. The other one that drives us to more balloons is FAA regulations and exempt, non-exempt conditions and requirements. So even up to the day of the launch, we might take a heavy configuration balloon and turn it into 2 light configuration balloons to cover that. So you could double the number of balloons in any one particular launch. So, EOSS will fly any one balloon with 2 beacons for redundancy. That's done for safety. Separate top and bottom beacons. The top beacon controls has a direction finding tone and other functionality, whereas the bottom beacon will often be a primary, but same frequency across the balloons, but time slotted. So you could have, with 4 balloons, you could have maybe 5 frequencies, or if there are different bottom frequencies for any reason, you could have presumably up to 8 frequencies at any one time. And so what you need is a capable way to track multiple beaconing frequencies in the 2-meter ham band simultaneously. The challenge with that, of course, would be the traditional analog approach. Each one requires a radio, 2-meter receiver, at least tuned to that frequency, followed with some sort of TNC. Now, of course, today you can get fairly, you can get combined units, radios together, but you're still talking about up to 8 perhaps, or maybe 5 serial COM ports. Of course, you can get USB versions of these and gang everything together. So we are talking about a lot of hardware, and typically in any one tracking vehicle, you might have a couple of radios or maybe up to 4 radios or so. But you're again dealing with a number of tracker vehicles and coordination of all this. Marty, of course, does a great job making sure everybody's got the right balloon and what balloon they're chasing and what frequency they need to be on. But a low-cost software-defined receiver could enable a real small form factor solution. That's kind of the goal here that I'm prototyping. So software-defined receivers and sort of a software-based approach, pretty straightforward. You have a piece of hardware that's essentially a very high-speed A-to-D converter and is effectively capturing and digitizing, in the case of the devices I'm using, about 2.4 gigahertz, excuse me, I wish, 2.4 megahertz of bandwidth, and capturing that, turning it into the in-phase quadrant data, like digital data, across that spectrum. It's really only effectively, sensitivity tends to roll off, so I generally, rule of thumb, use about 2 of the megahertz there, which is could be half of the 2 meter amp band, effectively. Once you have it in digital space, right, then software can take over, and you can parse out, you can burst out the frequencies of interest, 1 through n, and about the 25 kilohertz or so around each of the frequencies of interest, you can demodulate the FM that's on there. And what that'll do is that'll produce the audio frequency shift keying, or the encoded, if you will, signal in audio, a 1200 baud packet, and then you can decode that. You can detect and decode that packet and create the serial detection. So in principle, all you're limited by here is the ability of the processor software of the computer that this is running on to handle all that. And that's indeed the trade space that I've been experimenting with, very high-end processors or medium-end type processors, and down to the Raspberry Pi. Talk about that. What that looks like graphically, and John, you and I were talking about this a little bit. Grabbing here's 2 megahertz of bandwidth from 144 to 146 on one end to the other. There's a couple of FM signals on here, and then grabbing about 25 kilohertz around each of these signals centered on the frequency of interest, and then demodulating this FM signal here, basically. So as I say, the hardware grabs the entire spectrum across here, and then mathematically we carve out these 2 frequencies and the 25 kilohertz around them, and then additional software will decode that FM and feed it to an APRS decoder, packet decoder. The development environment of choice for any software-defined receiver really is a very well-maintained open source platform called New Radio. It's silent, and it's got a lot of advantages. It's quite a sophisticated package with huge community and support that built these modules. But it's a graphical environment in which you can develop SDR processing chains, and then what I use it primarily for would be to export that processing chain and the library modules into Python, and then I can run the Python on something like a Raspberry Pi or an ARM processor. You don't have to have this entire graphical environment on the Raspberry Pi, which would be quite taxing, but you can do all that development offline on a separate computer, and then when you get it working the way you want it, you can sort of export it, if you will, to something that can run on a Raspberry Pi. This is the parallel dissemination path, and then the FM modulator, narrowband FM receive function is here, and then it's creating the audio streams, which will then be picked up by another piece of software. I have to shout out to Doug Gentis, N0IX, who did a lot of this preliminary development. I've got his new radio rustling chain to be working quite stably. So back to this approach, what you see here is, so you have the hardware piece here. This is I'll describe the hardware a little bit later. This is the smart SDR. offered by a company called New NOO Electronics. There's the Python radio libraries running in software here that do this decoding. And then I use another open source fantastic development, Direwolf, which does the decoding. Direwolf has very good performance and able to pick APRS packets out of noise better than any other package out there. And then it creates as I say, each one of these creates the packet out serial text data for each of those regions. It's not very useful at that point, but if you add addition, so here's that processing chain I just described. If you add a local APRS IS server running, now you create a standard interface that pretty much any device, and furthermore any preferred APRS client software can connect to. This looks just like an APRS IS server on the internet, but it's locally hosted, and APRS Droid or TrackPoint or anything that conforms to APRS IS protocols can connect here and be served any of the packets that are being decoded coming in the Direwolf, just as if you were connected to the internet. And if the internet's available, say through a cellular modem or a local Wi-Fi, some maybe even a direct hardware connection, if the internet's available, then this APRS server can upload and igate those packets that it's receiving here, as well as feed other reported packets down to these clients. So it's very convenient. Additionally, if I add a GPS receiver and some GPS software running in the host as well here, then I can serve GPS information, NEMA sentences, for example, to any device on this net as well. So now, of course, most modern tablets and smartphones, they have their own GPS receiver in there. They don't need it, but some of the laptops, particularly student laptops, might not have a GPS receiver, and so they can take advantage of GPS information that's in here. Shout out here to Jeff Deaton, N6PA. He's been developing a very similar offline mapping capability that decodes and archives and creates a database of APRS. A lot of excellent work there. So in terms of the trade space, it starts to shake out a little bit like this, and my prototyping work has kind of rounded out the corners here. Single Raspberry Pi 3B+, which is sort of the latest 64-bit ARM processor that Raspberry Pi offers for about $30. You can find it $35. With a single SDR, one of these $25, $30 SDRs, will capture about half the 2-meter spectrum, 2 megahertz, as I'm saying. Provide both a connection up to the internet if you have a Ethernet or you have a Wi-Fi hotspot or Bluetooth of some sort, or a cellular data modem, and also allow users to connect to it as a Wi-Fi access point, if you will, or Bluetooth personal area network of some form, and all for about $70, minus the it didn't include the power supply, for example, or a motor. So it's got a lot of potential to be a very low-cost, small, compact form factor solution. Really only limited by the processing power of the Raspberry Pi, and in practice and demonstrated test, it's about 3 simultaneous frequencies stably for an occasional drop in packet. So if you can tolerate that, then that's 4 frequencies. You can gang a couple of the Raspberry Pis together and connect them via their Ethernet network, and then they can share the load. You can put an SDR on each one, and so you can double the number of channels and get into the range of sort of a maximum EOSS launch event. Cover the entire, you could cover the entire 2-meter band at that point because you can divide it into 2 halves. But you tend to, so now that you consume the network capability between those two, the hardware network, then you're limited to primarily Wi-Fi or Bluetooth connections between the devices and the client. You could tap into that network, although you're starting to push the limits of the network in terms of bandwidth. And then on the other end of the spectrum, sort of the Cadillac version here, right, the industrial, some sort of fanless industrial computer. I have an example of one here from Lots Supply here. And it's a real workhorse. It's a Pentium processor. It's the Apollo series of processors. It's got 4 gig of RAM in there. It's got a 64 gig solid state drive in there. So you've got pretty much anything you could want for testing purposes. And you can have as many SDRs on there as you want, practically, and you could put in all sorts of capability and ability to host internet and those sorts of things. But it's going to set you back something like $600. I've got 4 sort of example cases because this trade space really covers the spectrum of what we're trying to accomplish here. And so you can see kind of a range here, perhaps, across the board here. Everything from a single Raspberry Pi, ideally, with 1 SDR running in a very small sort of plug-and-play cigarette lighter enclosure. Students would hook up to it with their tablet or their laptop over Wi-Fi, and they'd run their favorite APRS client software and be able to tell kind of where the balloon is, all without internet, with or without internet, but out in the field, certainly. So, little mag mount antenna. I mean, it's a very nice little portable unit. EOSS trackers who want to use TrackPoint primarily, right, could potentially use 1 or 2 of the Raspberry Pis. Could potentially have backup power supplies, battery bank, a little bit more sophistication capability there. Another concept that we haven't tried yet, but would be interesting, would be setting up a unattended iGate somewhere out in the field on top of a hill near to the anticipated landing area or something like that. If it had a cellular modem and was within reach, then it could iGate out packets, effectively be left alone and then picked up after the launch event or the recovery. So. And then at the ground station, which is where I'm operating, I put basically all the bells and whistles in there, serving a public-private Wi-Fi, access to ground station clients, potentially iGating, driving a fairly large display, for example, which is typically what these some of these industrial computers are used for in kiosks. Quite a range of capability if investing in something that's pretty expensive. 2 more charts on sort of the hardware, and we'll get through this. Yeah, because the lunch has arrived. The Raspberry Pi, as I was mentioning, is this 3B Plus. It's the quad-core, but it does offer two wireless modes, both the 2.4 and the 5 GHz wireless, for about $35 or less. And then here's the new electronics, $25 SDR. This one's a bit better than some of the cheapest you can get them. And really, I drove this one for the metal enclosure, the SMA connector, and the oscillator has a 0.5 price per million. CCXO has a pretty good phase. So as far as the price to performance ratio, this is in the top. The fanless computer, as in contrast, is, as I mentioned, is this Pentium-based Apollo 8 processor running about 1.1 gigahertz with 4 gig of RAM in there and a solid-state drive. I got that from London. There are others, of course. On the software side, so here's the examples of some of the software. The radio, of course, I mentioned Direwolf, which is John Langer's WB2 OSN. His creation, well maintained, a lot of capability in Direwolf, but I'm using it primarily for the packet decoding and iGating effectively up to the client. The APRS server, IS server, is this is one that that basically one of the two available Java APRS would be the other one. OH7LDB out of Finland works on this one. So this runs, if I had to guess, I'd say maybe a quarter of the tier 2 servers on the APRS IS backbone run this software. This is all written in C. It's very lightweight, not a lot of bells and whistles. It's a neat configurability and all that. It's not the best choice, but it's very efficient and can run on the Raspberry Pi without necessarily taxing it. Java APRS, on the other hand, would require Java operating environment running on top of that. And then GPSB is a long-standing, it's included in most distributions of Linux these days. And it simply just looks for and takes any USB or serial GPS device receiver and makes the NEMA sentences available on the network. So, fairly straightforward piece of software. Okay, so last steps, where we're headed from here. First things first, I've got to get this stuff documented, my step-by-step instructions. So it will be going out on GitHub once I get all that. I've had to reinstall the software many times to get it configured, so I can do it with my eyes shut now. So. I think that perhaps the Achilles heel, right, the real challenge is everything's all command line right now, and scripts that I've written, shell scripts and text file, configuration files, and things like that. What I don't have is a nice GUI dashboard. Right? I even host a web server on here, a lightweight web server. So I'll be able to have web access to it from the device. But I'll need to write all that, and I'm not a graphic artist, so it's not going to look too great. If anybody wants to volunteer, I'll accept volunteers. And then I'd like to take it in the direction of that small form factor, single Raspberry Pi with one SDR. Make it sort of indestructible, plug into a cigarette lighter, and then have bring your own device, students with their capability, whatever laptop and software they want to run effectively. And that really would enable, I can envision some sort of deck out, or we have a lot of guest folks who like to come along and track, be able a way to receive only way in the cab of the car or whatever, or being able to track. I like the rest of this. That would be, I think, the next place to take the project. Good. All right. Lunch is set up, but I'm going to take any questions.
Can you hold up your prototype?
Oh, sure, yeah. Thanks, Nick. Okay, so two prototypes. This is actually the three Raspberry Pi variant, and this is more. Think of this more as a test bench. This is a standard 19-inch rack. Plastic enclosure. The real horsepower is this one down in the lower left here. It's the Raspberry Pi 3 Plus, and you see I've got a couple of those SDRs hooked up to it. The one in the middle here is more my supervisor. It's measuring the performance of the other two and operating sort of in a above the fray kind of mode there for me. So it's not really part of the end solution. And then the one on the far right is acting more as a local Wi-Fi access point and Bluetooth personal area network hotspot, taking advantage of that. So that's how I can get some connectivity into the system. So, and then I have an Ethernet switch in the middle here, a little 9-volt Ethernet switch, and allows me to get into the sort of inner network that I've set up between all these devices. Take a look at it. Okay. The other one here is this industrial computer. I just got it mounted to a piece of pine wood. But there's a fanless PC. As I said, it's an Intel Pentium style. It's the Apollo Lake processor in there. I've got a little GPS dongle, USB GPS type up that rides up there, and then just some power distribution so that I can run the devices off of there. So this one is the one we used on the way out. It was successfully iGating us all the way through Colorado and Wyoming and Utah. Other questions? No? Oh, yeah, sure.
So you said in the presentation you needed 2 SDRs for the whole 2-year spectrum. So you did 2 Pis. That one's got 1 Pi with 2 SDRs.
Right.
What's the difference?
Well, the difference would be in the number of frequencies. So in this configuration here, I can cover the entire 2-meter spectrum, 2-meter band plan from 144 to 148 if necessary. But I can still only on this one single Raspberry Pi, I can still only process 3 or maybe 4 channels. So EOSS and Nick have done a nice job of actually consolidating our frequencies for our balloons to within 2 megahertz bandwidth. And so, kudos to Nick for that. And what we can do is we can get by with just the one SDR. Then potentially I could get, again, the 6 frequencies, sort of bare minimum.
We should point out that I did a little bit of some of the administrative work for that, but Steve Meir, with a very sophisticated interface program, actually drove down to the 3-digit 2-meter frequencies that didn't interfere with each other with cross modulation like the 3rd and 4th line.
Yes, very good point.
For the real tough work.
So what Nick's pointing out is we wanted to standardize the frequencies, and they're all within, as I said, within the band plan and within 2 megahertz of bandwidth within that window. And but what Steve did for us was make sure he checked all the harmonics, checked all the co-interference potential, and helped us sort of dial in those frequencies so that we would step on each other or create sort of harmonic spurs. So yeah, so kudos to Steve. Seems to have escaped. So probably had a phone call. But yeah. Nick, honestly, I don't know. That might be worth publishing. I'm not sure what the sensitivities are. I know to try to not make broadcast our frequencies so that we don't have the occasional person stepping on us or anything.
We can certainly make that available to anybody in
Yeah,
the living community who's interested, but you've got to remember it's against the Colorado band plan.
Okay. Good point, yeah. All right.
You
Okay.
can email me and we can share it.
Any other questions? All right, well, great. Thank you very much.
I guess let's do one more drop before we do lunch. Rach, if you want to go ahead and pull the next one out.
Hey, Jeff, did you bring your stuff over and zoom in on?
So, 7 items still remain. All right.
Jim.
Hello?
See if we can.
There you go. Can we pick one that's already been picked?
All right, the ticket number I have is 361, or the last 3 digits, 361.
361 did not put a name on it.
Oh.
Okay, all right.
You're doomed now.
Okay, with that, I've got a list out of what everybody wanted in case you don't remember. Everything is stacked up by type, solar.
Okay, comments online. I sent it.
So, one
No, I
more
agree.
please. We've got drinks, we've got your salads, you've got your sandwiches. Please come on around and have Rach crush out and pick up a meal, please.
Benji, how come you're hobbling?
Yeah. So it's again when I get back.
Okay.
I fell down a while back.
Good.
I've probably done all the websites. Okay, but I guess that's the question I had.
I'm not sure, yeah, probably.
Yeah.
Post them on.
Probably post them on the website.
No.
Yeah. Yeah. But we can coordinate. Yeah, we gotta play around. Get started. Okay. I've been building step by step. Okay. So, the operation. All the drivers. Yeah, so it's all. Yeah.